Hello students, in this lecture we are going to study about equivalent relation. Usually the kind of attention that we pay to other core topics of algebra and calculus. We usually underrated the topic of relation. So without any further ado, let's get started. A relation is said to be equivalent only when a relation is reflexive, it is symmetric, as well as it is transitive. So what these relation are? So let's study one after another one. Hello student, welcome you all on Kota Scholar. So in reflexive relation, a relation R in a finite set A is said to be reflexive only if every element of set A is related to itself. Suppose if we set A contains some finite number of element A, B, C. So if element of A are associated to itself, only then relation is said to be reflexive. Otherwise, no. For example, say we have a set A containing these three elements P, Q, and R. So if we are looking whether a relation is reflexive or not, then obviously we are looking for ordered pair, likewise P comma P, Q comma Q, and R comma R relation of elements with itself. So if you look at these relation R, Q, and S respectively, in relation R, we have PP, QQ, and RR as ordered pair respectively. In relation R, there are some other uninvited guests, P related with Q as well as Q related with R. It's not our problem actually, since if elements are associated to itself, then your relation is qualified to call a reflexive one. Wherever in Q, a relation of element Q with itself is missing, thereby thereby relation Q is not said to be your reflexive relation. Similarly, R is said to be a reflexive relation because every element of A is related to itself. Let me take another example for a better understanding. In this one, just have a look on the first one. I have defined this relation using set builder way. A definition of relation R1 is given which bind element X with Y such that X is divisible by Y. So if X is divisible by Y, if you are looking for whether a relation is reflexive or not, that means you usually want to check whether this element, one with itself, two with two, three with three, so on and so forth, whether these elements are divisible by itself or not. Obviously, any natural value is divisible by itself, so it will make your relation reflexive. I'm sure you understand it right now. Now have a look on the another one for more clarification. Set S contain all the line in a plane. Right now we are talking about two dimensions only. In the first one, line L1 is related to line L2 such that from relation R2 such that L1 is parallel to L2. So if L1 is parallel to L2, you are looking for whether a particular relation is reflexive or not. For your relation to be reflexive, line L1 should associated with itself with the relation R2. According to that one, your line L1 must be parallel to itself. So what do you think about it? A line, whether it is a parallel to itself or not? If yes, then obviously your relation is reflexive. As we know, two lines which are parallel to each other, a coincidence lines are also known as parallel to each other. So that means your relation number 1 or R2 is also said to be a reflexive one. Wherever R3, it bind the line L1 with L2 such that both the lines are perpendicular to each other. Right there, if I ask you whether this relation is reflexive or not, that means you are looking after for a particular line L1 such that it is parallel to itself. Now, how can a particular line can be perpendicular to itself? We know if both the lines are equal, then lines are said to be coincident, not perpendicular. So your third one is not a reflexive relation. And the next one, if A is the brother of B, then how is it possible that A is become a brother of itself? So it is not possible. That means your relation is not reflexive. Now have a look on the another one, identity relation. It look resemble as of the former one, but with a very minor difference of letter only. In that relation, every element of set A is related to itself only. So just Have a look on this example again. Again, we have a couple of element in set A and three relation are given. Relation R, Q, and S. And relation S, elements are associated with itself only. So S only is said to be your identity relation. Wherever in relation R, elements are obviously associated to itself, but there are some uninvited guests which we don't want to. So just because of this element, your relation is not identity. Similarly, if, since Q comma Q is missing, relation Q is not a identity relation. After that, we have a symmetric relation there. Symmetric relation when if elements A1 comma A2 which belongs to set A, if are associated with the relation R, so your relation is said to be symmetric only if there must be element A2 comma A1 in the same relation R. Or you may also define it with a symbol. The way A1 is related with A2, A2 must related with A1 with the same relation R if you want your relation to be symmetric one. For example, say if I have these couple of ordered pair. And the first one, the way one is related to two. So you have to look after for element like 2 comma 1. The way 1 comma 2 is related, there should be a 2 comma 1 there. So if there is a 2 comma 1, your relation is said to be symmetric one. In the next one, only a single, it's a singleton set, 1 comma 1 is what participating there. That means the way 1 is related with 1, obviously 1 will also related to itself. That means the relation is a symmetric one. And the third one, we have 1 comma 3 as well as 3 comma 1. But for the element 2 comma 3, we don't have any counter element like 3 comma 2. So the third one is not a symmetric one. Fourth one is by default a symmetric relation since it's a empty relation, and every empty relation is said to be symmetric one. Fifth one is not a symmetric relation. Why? Because 1 comma 2 is there, but its counter element 2 comma 1 is missing from this relation. So this is not a symmetric relation. Now let me take some more challenging problem just to get a great insight of symmetric relation. In this one, relation R1 which bind elements from set A to some other set B where both elements are taken from natural number. So if x divides by y, that will make your x is equals to some integral multiple of y. Am I right? So you just need to tell me, is it possible to bind element y with the same relation R1 with element x? That what I want to convey there, you know that 2 is something which is divisible by 1. So can you say that 1 will be divisible by 2 if 2 comma 1 is a particular element is there? So will 1 comma 2 will also associated with the relation R1? If yes, then your relation is symmetric. But this is something which is not possible. As we know that if x comma y is something which belongs to integer, that means y comma x is not possible that this will give us a integer only. Except some special case when your x and y will take the same values, this is not possible. Now have a look on the next one. A set of lines in a 2D plane. Relation R2 is given such that line L1 is line L1 is parallel to line L2. If both the lines are parallel, swapping the position of L1 and L2, I would say, or I just have to prove that L2 is related with L1 in the same manner as of L1 related with the line L2. So it does implies that we need to prove that line L2 is parallel to line L1. We already know that line L1 is parallel to line L2. Swapping their position will not affect their condition of parallelism. So obviously this relation is said to be symmetric one. In the next one, where lines are perpendicular to each other, swapping their position, or what we need to prove that L2 is related with line L1 in the same manner. That means we need to prove whether line L2 is parallel to line L1 or not. Obviously, if L1 is perpendicular to L2, then L2 will also be perpendicular to line L1. In the next one, A is a brother of B, but right now, right there, we don't know what B is. B may be a sister or it may be a brother. So if it is given that A is a brother of B, you need to prove that B is a brother of A. Then this is something which is not possible, because right now we don't know anything about the gender of B. It may be B may be a female or it may be a male. So your third relation, sorry, your relation number 4 is not symmetric one, because there are multiple possibility there. Now, let me move to the last one. It is a transitive relation. For transitive relation, we need at least three elements to prove whether a particular relation is transitive or not. Now, how transitive relation does work? A particular element will obviously given to you, A comma B is associated with the relation R. You need to assume it by yourself that in the similar way, there will be a element B comma C which associate with the relation R. And based on this assumption and given data, you need to prove that A comma C belongs to R. If you successfully prove that A comma C is the part of relation R, then there you go, your particular relation is said to be transitive one. If you can't, then your relation is not transitive relation. For example, let me take this example right there. In relation number, let me take relation number 3 first of all. Two elements are there. We have A comma A as well as we have C comma D. But right there isn't anything to commute. What do I mean by commute? See, already A comma A is there. The way A comma B is related with the relation R3, there should be a relation, there should be a element, excuse me, B comma C, which should relate with the same relation R3. But unfortunately, in this relation, counter elements, or you may call counter ordered pair, is missing. So by default, your relation number C is set to be transitive one. To understand your part C in detail, let me go back to this slide with a bunch of questions which will help you out to understand that particular thing. Say if I have element x comma y belongs to natural number such that x is divisible by y. So if you find it difficult to calculate in variable, you may assign some particular values to x and y. But if you feel comfortable in x and y, then go with the flow. It is given that if x is divisible by y, that means we can express x in terms of integral multiple of y. So there we go, x is equals to lambda times y. It is something which is given. Based on this assumption, you need to consider, you need to assume that with the same relation, element y will be related to element z, such that y will be integral some other integral multiple of z. So this is your relation number 2. Based on your relation number 1 and 2, you need to prove that with the same manner x must be related with element z. So how effectively you can use your relation number 1 and 2 will give you your response. So if you just try to multiply these two relation 1 and 2, either you multiply or divide this expression, you end up getting x y is equals to lambda times y times mu times z. From there, your y will get cancelled out since y is a non-zero value. So we end up getting x is equals to some integral multiple of z, which prove that x is divisible by z. If you don't want to deal with these symbols, then you may assign some particular values to x, y, and z. Say if x is divisible by y, you may consider that x will take a value equals to what, 8, and based on this value you need to assign some values to z. So say if you are assigning z, or you are considering that y is equals to 4, since we know 4 totally divide your number 8. Now based on these given data, you need to consider z by yourself such that z divide y completely. So what values of z will be, it depends on you. You may consider z can be equals to 1, or even you may consider z is equals to 2. So if you are taking some other values apart from x and y, let it be 2. So you need to prove that 2 completely divide 8, which is a obvious thing. So thereby we prove that your relation number 1 or relation number R1 is transitive one. Just try to understand the next one for the better understanding. Again, you need to prove your relation R2 is transitive one. It is given that there is a line L1 which is parallel to line L2. You need, or again, after this given data, we some data is something which we need to assume, and say there is a line L3 also there which is parallel to line L2. So if L1 is parallel to line L2 is given, L2 is parallel to line L3 is what we assume. So based on this data, can you prove or can you understand that line L1 will be parallel to line L3? If it is an obvious thing, then this relation R2 is said to be transitive one, otherwise named. Now, have a look on the next one. L1 is related with R3 with line L2 such that both the lines are perpendicular. Right now, we are talking in 2D only. So just draw two perpendicular lines. Say we have line L1 which is perpendicular to line L2. This data is something which is given. Now you need to assume a particular line L3 in a way that it is perpendicular to line L2. Suppose this is your line L3 which is perpendicular. Perpendicular means angle between the line should be 90 degree. So based on your design data, can you prove that line L1 is always perpendicular to line L3? But right here in picture, it is completely different. Here we are getting line L1 is something which is parallel to line L3. So if we are getting something which is opposing our data, that means your relation is not qualified to call transitive one. So this relation is not transitive one. Correct. Now let me move back to the slide which we are already discussing. Your empty relation will always be a transitive one, just like it is a symmetric one. If we don't have any in ordered pair, if we don't have any counter elements, then you have to declare your particular relation is transitive one. But what about D then? In D, element A comma B is there. So you need to check whether B comma A, whether the way A comma B is related, A comma B belongs to relation R4. Is there any other element which initiate with V and related with the same relation? Just have a look on the second element, what message I want to convey to you. In that one, your B is related with A, B is related with A with the same relation R4. So just we need to prove that whether or not there is an element A comma A in that relation. As you find out, A comma A is already there in this relation. Your relation is qualified to call transitive corresponding to element A comma B. Just try to understand this statement again. See, if you have an element B comma A, if you have an element B comma A from relation in relation R4, then you need to check any other relation whose first element is A. There are multiple one. So first one is your A comma B. So I know there is another element A comma B also belongs to relation number R4. So to make a transitive relation there, you need to check whether B comma B, if you just check the second and first position of element there, then based on this cancellation law, you need to prove a particular element B comma B belongs to relation R4 or not. As we can see, since B comma B is missing out from relation R4, so your relation is said to be not transitive corresponding to element B comma A. If your relation is not transitive, even corresponding to a single element, your relation is qualified to call not transitive. This is said to be something which is not transitive. I hope you get a bit insight of this kind of relation. In the next lecture, we'll be discussing about a more bunch of question based on equivalent relation. Thank you very much.